Introduction to Gear and Gear Unit Design. This is module 1, and the second lecture of module 1 is on laws of gearing, kinematics and geometry, part 1. In this lecture, I shall cover fundamentals of gear tooth profiles, next gearing laws. Let us consider the cross belt drive with flat belt. There is a small drum which is usually driving, may be driven also, and a big drum. It might be equal also, size of this drum may be equal also. However, this is the belt, cross belt, and let us consider a point at the tangent of the belt with this drum. Then this drum is rotated in clockwise direction, and due to this motion, the belt will move in this direction and the other drum is moving in anti-clockwise directions. Now, this point gradually moving towards this clockwise direction on the drum, and on the belt it is coming towards this point. Now, after certain rotation, this point will come here, whereas on the belt this point will come at this point 1 dash. Now, if we consider the each and every point and draw a locus, then we will get this profile on this drum. Similarly, if we consider the point 2 in other drum, and if we rotate in the opposite direction, then we will get, when the point 2 will reach at this point, we will get a profile which is nothing but the locus of these points as it is travels. So, this means that we are getting these two profiles on this drum due to this motion. Now, if we remove this belt and allow these two profiles to touch each other, and then again if we consider the first motion, the motion will be exactly same as it is with this belt. This means that this cross belt drive can be replaced by these two drum with these two profile. So, therefore, this is, we may consider the first concept of gearing, how we can come into tooth gearing for power transmission. Now, as you know, on a circle, if let us consider this is a thread is unwound, then the curve generated on this point is called involute. So, therefore, this must be involute, but the question is that in case of belt drive, we get a continuous motion as belt is a closed loop, but how we can get the continuous motion with these profiles? The obvious alternative is that we should have such profile at certain interval, and that interval must be uniform, and then if we can make these drum with these profiles such that when one is disengaged, at least another one will be engaged, then we will get the tooth gear. Now, what I have shown, that is the generation of involute, but also we can transmit the motion between two drums from one to other by using 3 drum. Let us consider this is a hollow drum and this is a solid, maybe hollow also, but what we are doing, we are using another cylindrical body on the top of this surface, which is touching the inside of this surface. This means that this cylindrical drum and this cylindrical drum, they are touching each other, the outer line will touch each other, and this drum is touching inside and this inside of this bigger drum and outside of this smaller drum here. Now, if we consider a point on this, then if we rotate this roller and then if we take a point on this, then this point will generate a profile inside as well as outside, because this is the same way as I have shown in earlier case. If we consider the locus of the point on this drum and while it is rotating on this drum, then it will generate a curve. Now, this curve which is generated on these 2 drums, when it is rotating inside, it is hypocycloid, this is rotating outside of a drum, that is epicycloid, and inside of a drum, that is hypocycloid. And in that way we get also a profile which can be fixed on these 2 drums, and this can be replaced and we can transmit the motion. Now, this is another gear, another profiles for the gear, which is called cycloidal profiles. So, what we have seen, that we can use the involute or we can use the cycloid to transmit motion from one drum to other. So, definitely these 2 can be used for gear tooth profile. However, here question is that is these 2 are the only profiles? Answer is no. There are many other profiles which must be conjugate and we can use as a gear. Actually, if we fix any curve on a drum and while we rotate one drum touching other, then or maybe with the cross belt, if that attached profile generate another continuous profile, then that must be conjugate and that can be used as a gear. Now, the question is that whether shall we use all such profiles or we should be selective, or is there any other reason that we have to stick to few of the profiles. So, I will come to that. Now, I have shown how the involute is generated. Now, this involute profile is fixed on the drum on which it is generated, and then that gives a gear tooth profile. Now, definitely as I told that we have to use the profile one after another on the drum at a fixed distance, then that will give the continuous motion. So, a tooth will look like this, involute tooth will look like this, which is generated on this on a drum, and if we consider a tooth that should be of a specific size, the size should be such that when one pair is out of touch, then other pair will be engaged, and in that way, say this is being unwinded and this profile is being generated, and we consider the tip circle which is called addendum circle, and this is called pitch point. What is pitch point? I will come later, and this is called pitch circle. Pitch circle is a reference circle which will be there when two gears are rotating and there the common circle which is touching each other. We shall come later on to that, but this is called pitch point. It is on this line, and this is called base circle on which this profile is generated. However, this tooth may be below the base circle, although this portion is not involute, then this circle is called either dedendum circle or root circle, but this portion is not used for tooth contact, only it is used for the clearance. Similarly, so this is called pressure line or line of action which passes through this pitch point. Now, this if we this is the involute, and this angle is 90 degree and this angle is alpha is called the pressure angle. If we consider another gear is mating, then this line will touch the base circle of the other gear, and we would call that this is the line of action and this would be the pressure angle. In case of cycloidal tooth, these two are generating circle. These two circles are generating circle as I have described in the earlier slide. So, that will give us this type of profile, which in open eye may look like an involute profile, but there will be obvious difference also. Now, this in this case, in case of cycloidal tooth, this circle is called, this circle itself is the pitch circle as well as base circle, whereas it is not called base circle, it is called describing circle, whereas in case of involute teeth, this is called base circle, that is the basic drum on which this involute has been generated. And this is epicycloid and this is hypocycloid. So, I have shown only two profiles, involute and cycloidal. As I told, that other profiles are there, but we are not, we will consider only the involute profile. Why? For that, let us look into this gearing law. Now, what is the basic purpose? We are transmitting power from one to other. Power means the speed and the torque. When the speed increases, torque will reduce, and usually in most of the cases we will consider there should have the constant reduction or constant increase in speed or torque. Usually the prime mover through which the drive gears is connected, that is of constant speed, and output will be also constant speed. This means that the ratio of this gear, ratio of this basic drum, ratio of the describing circle should be a constant. Now, we shall examine that through a gearing. Let us consider these two are gear profiles. These are two gears, gear 1 and gear 2, and then this profile has come to a contact point which is K1, and then if we consider the gear 1 is rotating at omega 1 speed, then we can draw a vector, the velocity vector, which can be written k1 m1 is equal to omega 1 into O1 into k1. Here I would like to mention that this angle is 90 degree, because as we are presenting in this way, this is 90 degree. Although we have this is not proportionate, but consider this is 90 degree. Similarly, k1 m2 for the rotation of the gear 2 will be omega 2 into O2 k1, and this angle is also 90 degree. Okay. Now, if we write this equation and consider divide one by other, second one by the first one, then omega 2 omega 1 is equal to k1 m2 by O2 k1 into O1 k1 into k1 m1. This can be easily derived. Now, now as this, if we consider the triangle, then O1 k1 a is similar to k1 n1 m1, because this angle is alpha angle, and as this has rotated by this amount, then this angle must be equal to this angle. So, these two are similar triangle, and due to that we can write O1 k1 is by k1 m1 is equal to O1 a by k1 n1. Similarly, if we consider the other circle, then k1 m2 divided by O2 k1 must be equal to k1 n1 is O2 b. This means that if I consider omega 2 by omega 1, then O1 a divided by O2 b, and again from the similar triangle property of this O1 a p and O2 b p, we can write this must be equal to O1 p by O2 p. But these two are nothing but the center distance, and these two gears is always have a common circle which is touching at the point P, which is nothing but the pitch circle, and therefore, this ratio is always constant. Therefore, if omega 1 is uniform, omega 2 will be uniform with a constant ratio. So, this is the basic laws of gearing. Now, here interestingly, we can look into this as this velocity vector is having a common projection k1 n1, and this one also has a common projection k1 n1. That is why the velocity remain constant. This line velocity along the line of action remain constant, and this ratio remain constant. But if we consider their component along the k1 directions, one is k1 t1 and another is k2 t2. Obviously, these two vectors will be same equal at the point P, but other points there will be difference. This means that while this tooth contact, consider this is the involute profile, this is giving a constant velocity along the line of action, but they are having a rubbing action on each other except the pitch point, that due to this rubbing on these teeth there will be some losses which can also be calculated. So, For gearing, this should be maintained. Now, it can be shown with the involute teeth, this is easily maintained. It also can be mentioned here. In case of involute teeth, we have this line of action is a straight line, which is nothing but the cross belt, you can say that, like a cross belt. But in case of cycloidal tooth, that path is carved, but still with that carved and if we draw the geometry, the same thing can be proved for cycloidal tooth also. Now, if we compare the tooth profile of involute and cycloidal, then in that case what we find, the line of action is straight in case of involute, whereas in cycloidal it is curved. Radial component of normal load, if we consider the normal load, that definitely will act through the line of action, that will be radial component will be constant in case of involute, but as the path of contact is curved in case of cycloidal, that will vary. What does it mean? That in case of involute tooth, the radial load which is going to the shaft will always remain constant for a constant torque, whereas in case of cycloidal tooth, for a constant torque, that will vary. Now, effect due to change in center distance. If you change the center distance in case of involute teeth, what we find that there is two base circle. This base circle is being driven by, say, like a cross belt, that is there is a common tangent. That means, if we even if we move these 2 points, but still the same involute will touch each other, and therefore, gearing laws will remain unaffected. Whereas, in case of cycloidal teeth, gearing law will be violated, because as long as if they are moved, then the two describing circle, they are away from each other, and this at that portion the gearing law will be violated. Now, if we consider the beam strength, in case of cycloidal tooth has better strength capacity, that is from the geometry it can be proved, there will be from more or less same size of teeth, the cycloidal tooth will have better strength, whereas in case of involute tooth the strength will be less. Now, tooth generation, involute tooth generation is easy and less expensive, and definitely cycloidal tooth generation will be relatively expensive. Interchangeability, in this case, as we find that the common tangent is generating the involute tooth profile, then definitely if we can change the size of the drum, that means there will be interchangeability, whereas in this case the two touching circle generating the cycloidal profile, and we cannot interchange. So, always these gears, cycloidal gears, has to be manufactured in pair, but still I would say that cycloidal tooth are used where for a special purpose, and that has a specific purpose and some certain advantage as well. Now, interference and undercut, this I will discuss later, what is called interference and undercut, that occur in case of involute teeth, whereas in case of cycloidal teeth this will not occur. Now, ideal properties of geared tooth profiles should be like that: constant velocity ratio, relative motion and rolling in nature as much as possible, although there will be slide which I have discussed, more than one pair to be in contact, and cantilever beam of uniform strength. That should be ideal geared tooth profile. Now, profile other than involute, as I have discussed, profile may be anything provided it has a realistic conjugate profile. However, from manufacturing point of view, very few are feasible. Tooth profile, cycloidal, novicom, etc. are special cases. Novicom is another type of profile which is also used for gears. However, it is found that among all, involute is the best, and our gear design, what we will learn now onwards, that is mostly on involute gears. Now, if we consider the involute tooth terminology, because we should know something more about the laws as well as the gear geometry and kinematics, but before that it is better to know what are the different terminology used in gears. Here I have drawn two involute tooth profiles, and then this is the face width of the tooth. This is sometimes it is called tooth width, sometimes it is called the gear width. This width is from one side of the gear to other side, that is called face width. Now, this portion is called top land, and this circle is called tip circle, or as I have mentioned earlier, addendum circle. This surface is called face, and this portion is called flank, the below this pitch circle. Now, this portion is called bottom land. This circle is called pitch circle. Now, definition of pitch circle is that if we consider the involute tooth, then two base circle a line can be drawn through the base circle which will touch two base circles. Now, that will intersect the line joining the centers of these two gears. That point is called pitch point, and the circle through these pitch point is called pitch circles. So, pitch circle physically there is no existence. When the gear mesh, then we will have the pitch circle. Okay. But in standard gears, we take the standard cutter, and when we with the standard gear, when we make the standard tooth, then the proportion is such that this becomes the circular pitch and this gap equal to this gear width. Okay. It is not proportionate, looking proportionate here, but we have to remember for standard gears on pitch circle, this arc thickness of the teeth is equal to arc thickness of the gap. So, this is called tooth thickness, this is called width of space. These two are equal for the standard cut gears. Now, this portion is called addendum. We should remember this height is called addendum, and this portion is called dedendum, and this is the base circle. No, this point is called at the root. This is called fillet radius. This is also called root, and this circle is called root circle, or sometimes called dedendum circle, root circle or dedendum circle, and this is addendum circle or tip circle, and then this clearance, this is called clearance circle. Now, this clearance circle not necessarily the base circle, rather if we consider the tip circle of the mating gear, that will pass through this point, that will touch here. So, this portion is called clearance circle, clearance. Now, this clearance, this if we consider now base circle, usually base circle will be below the clearance circle. Now, for this portion which I have delivered, you can follow a book, The Design of Machine Elements by Spot. Now, this I have followed the third edition, but it is available, the later editions are now available. Now, there is another very good book by G. M. Moitra, Handbook of Gears, and there many informations or gears are there. Apart from that, there are many other books which some of them I have mentioned in my introductory lecture. Thank you.